Muscles can change the shape of the body, but internal movement alone cannot propel the animal. Every snake must solve the same mechanical problem. Where should the body grip? Where should it slide, and what can it push against? The remarkable part is not simply that snakes move without legs, it is that the same body can transform into several different locomotor systems depending on the terrain. The foundation of this ability is the snake's elongated skeleton. Depending on the species, a snake can possess well over 300 vertebrae, with ribs attached along most of the trunk. Instead of a few large body sections controlled by limbs, it has a long sequence of small, flexible segments. Overlapping muscles connect the vertebrae, ribs, and skin, allowing different regions to bend, stiffen, lift, or pull independently. The broad scales covering the underside of the body are also specialized for contact with the ground. In many species, these ventral scales slide forward more easily than they slide backwards or sideways. The difference is created partly by their shape and microscopic surface structure. However, the scales are not wheels, and the ribs do not simply walk like hidden legs. Forward movement comes from coordinated muscle activity, interacting with friction and the surrounding terrain. The basic physics is the same as walking. A human foot pushes backwards against the ground, and the ground pushes the body forwards. A snake must create the same reaction force, using bends, scales, and different regions of its body. The most familiar method is lateral undulation, the classic serpentine movement usually described as slithering. A wave of bends travels backwards from the head towards the tail. As the wave passes down the body, different sections press sideways against stones, twigs, vegetation, and irregularities in the ground. Each contact produces a reaction force. Part of that force pushes sideways, but part of it points forwards. The sideways forces from different bends largely oppose one another, while the forward components combine to propel the snake. The snake is therefore not moving forward simply because it is waving from side to side. It is using the wave to position sections of its body at useful angles against the environment. This also explains why a snake can move efficiently through dense grass or narrow gaps. During low-slip lateral undulation, each section of the body follows roughly the path taken by the section ahead of it. The head finds a route, and the rest of the body flows through nearly the same space. Visible rocks and branches are not always required. On relatively flat ground, differences in friction across the belly scales can still generate thrust. They can redistribute their weight, pressing some regions firmly against the surface while unloading others. On an extremely smooth surface, however, useful friction becomes harder to generate. The snake may continue producing body waves while making little progress because there is nothing substantial for those waves to push against. In water, the same general traveling wave system operates differently. Instead of pushing against fixed objects, the snake accelerates water backwards and sideways. The reaction from the water pushes the animal forwards. The body wave travels towards the tail faster than the snake itself advances, creating the slip required to generate thrust. Lateral undulation is fast and versatile, but it requires enough space to bend. Inside a narrow tunnel, a snake may be unable to form broad sideways waves. It can then switch to concertina locomotion. The rear portion of the body forms tight bends and presses against the tunnel walls, creating an anchor. The front of the snake extends forwards, forms a new set of bends, and establishes another anchor. Once the front is secure, the rear is pulled forward. The process resembles extending and compressing a concertina. Anchor, extend, anchor, and pull. This works in spaces barely wider than the snake, but it is relatively slow and energetically expensive. But in a confined tunnel, it may be the only workable option. A related method is used when climbing smooth branches. The snake grips part of the branch, extends its front, establishes a new grip, and then pulls the rest of its body upward. Loose sand presents the opposite problem. There is plenty of space, but the surface gives way when pushed too hard. Ordinary undulation can cause the body to slip and dig into the sand rather than move forwards. Desert snakes solve this using sidewinding. Sidewinding combines two waves traveling along the body at the same time. One bends the snake horizontally, while the other lifts and lowers it vertically. Because these waves are offset from one another, some sections remain stationary on the sand, while others are lifted, moved forwards, and placed down at a new location. The regions touching the ground act like temporary feet. They do not slide continuously across the sand. They remain almost stationary until they are lifted and replaced. The snake consequently moves at an angle to the direction in which much of its body appears to point, leaving a series of separated, roughly parallel tracks. Lifting much of the body reduces drag and limits disturbance of the loose surface. It also reduces how long any one section remains in contact with hot desert sand. When climbing a steeper dune, sidewinder rattlesnakes increase the length of body contacting the ground. Spreading the load across more sand prevents the surface from collapsing beneath them. Researchers have reproduced this strategy in snake-like robots, allowing machines that initially failed on dunes to climb much steeper, sandy slopes. The strangest major form of snake movement may be rectilinear locomotion, because the snake can advance without visibly bending at all. This is often seen in heavy-bodied snakes such as boas, pythons, and vipers. From above, the body appears to glide slowly forwards in a straight line, while waves of movement pass through the skin beneath it. During this movement, muscles connecting the skeleton to the skin pull sections of the belly skin forwards. Those scales then make firm contact with the ground and stiffen. Other muscles pull the skeleton and the rest of the body forwards over the anchored skin. The scales are then released, moved forward, and planted again. Because different regions are at different stages of the cycle, some scales are gripping while others are being repositioned. The snake's main body can continue advancing even though parts of its skin repeatedly stop against the ground. It is less like walking on ribs and more like moving over a living conveyor belt. The skin itself transmits the propulsive force. Rectilinear movement is slow, but it has several advantages. It works in confined spaces, requires almost no sideways movement, and allows a heavy snake to approach prey without the obvious sweeping motion produced by normal slithering. These categories are useful, but real snake movement is not limited to 4 rigid settings. A snake crossing uneven terrain can assign different jobs to different portions of its body. When climbing a large step, the lower body may undulate for propulsion, the middle may stiffen and bridge the vertical face, and the front may begin undulating again after reaching the upper surface. Brown tree snakes have even been observed using a 5th method called lasso locomotion. The snake forms a single loop around a wide, smooth pole, grips it like a lasso, and sends small bends through the loop to inch upwards. The method is exceptionally slow and strenuous, but it allows the snake to climb cylinders too wide for ordinary concertina movement. This flexibility is why engineers study snakes when designing robots for pipes, collapsed buildings, and rough terrain. Copying the shape is relatively easy. Reproducing the snake's ability to detect contact, adjust pressure, and change its movement from one body region to another is much harder. A snake does not possess one single replacement for legs. On ordinary ground, its body becomes a traveling wave. Inside a tunnel, it becomes a series of anchors. On loose sand, it lifts and plants sections like temporary feet. During rectilinear movement, its skin becomes a moving track. Snakes do not move despite lacking legs. They move by turning almost every part of the body into something a leg would normally do.